There it is. Can y'all hear me?
Yeah.
Good afternoon. My name is Cameron Lewis. I'm a PhD student at Howard University. I'm going to present about my topic. Title really quantum corners. It's a prototype for my research, but it's about improving emergency response with smart traffic management and quantum sensors. So, this real quick, just to get your eyes looking at something like I talk. I drive a lot. This is currently over on Wisconsin on East Street, and every time there's always traffic. Emergency vehicles want to try to come through that small little pathway, and it's always just a lot of traffic. And I would say, like, at first you can be annoyed, but when you really think about it, this is actually a very vital problem. Imagine someone trying to get to an emergency and they can't get through because of just small lanes that we see normal here, especially in Washington, D.C. So, from seeing that, I've seen this as a problem, and I started off my motivation of wondering, you know, we see emergency vehicles stuck behind halting traffic on their way to these emergencies. So, just being in the field I am technology, I want to know, is it possible to use quantum sensing to improve the emergency response with just our current capabilities that we have right now? So I said, I believe that using a commercial off-the-shelf LiDAR, literally another properties of light, it could be the foundation for a quantum sensing system to see if we can tackle the emergency response problem. So I came up with the idea with a little bit of help from my research friends, quantum coordinates. So it's a transverse application that has three parts. The first is the quantum sensor, which is based off of the quantum LiDAR, the single photon detector. Then we have quantum communication, quantum computing, which is going to be based off of quantum SLAM, which would be the SLAM algorithm augmented with quantum principles. And then lastly, quantum communications with quantum optical communication. Probably going to use quantum key description for that. But let me get to talk about the background, how we got to here. So my background, I'm not a quantum physicist or a scientist. I am actually a hardware guy. So my background is electrical computer engineering. And so I started off a lot of my research looking into the simultaneous localization of mapping algorithm. It is for users for robots, and the biggest problem with SLAM is looking at the window adjustment. That's that circle part right there at the very end. That is the most time-consuming part of the entire algorithm. That is our bottleneck. So, when looking at window adjustment, there actually is the window adjustment problem. So the window adjustment problem is basically I have a scene, I have an object in 3D space, and I want to recreate that figure to get the coordinates to give it map my location. So what I'm doing is I'm taking images of that figure in multiple frames and then extracting those points and then just comparing them between each other. They have to be in a whole bunch of keyframes, map points. So once you have that, you get down to basic math, which is actually a cost function. That's called function. It's really not difficult to solve, but it takes a lot of time to solve in computers. We use that by solving a quad algorithm, which is an enabling algorithm, so where you just kind of differ the parameters to figure out you're doing gradient descent if you're farther away from the answer, but you're also doing Gaussian for close to the answer. So going back and forth between those two. Now, in the software profile, which I have below, the Jacobian update and the Skirt complement are like the two most ones that take the longest time to actually create this algorithm. Some of the solutions that I've done trying to fast make this algorithm valuable to the real world applications is putting those two parts of hardware, doing some software parallelization as well. But a lot of those algorithms have not been shown to do the best job at actually accelerating the window adjustment algorithm. So, when I look at this visually, I also teach 7th grade math, so I've been doing a lot of geometry stuff. But I look at this visually and I see a graph. If you look at a graph, why are we doing what is complicated math? We can actually now, with the capabilities we have, train on the graph. So, this is a graph that Aaron right here put together based on the keyframes and the map points. So this graph right here relates to where we relate the keyframes from the pictures to the map points that we actually see. Once we have that graph, we can actually look into graph neural networks. So graph neural networks is where you take an input in the graph, pass through the graph layer, and get an output graph. Taking that concept, we can create, this is from the actual paper that we actually did this, a graph neural network block. So now we're training the initial picture that we have, going through multiple steps. Instead of doing any math computation, we're actually just training on that graph to get the actual answer and optimize the problem. So from there, I was inspired to go ahead and state the problem that we have to bottleneck, which is in window adjustment. But can I create a base hardware-based graph neural network on FPGA to serve as a computational solution for foundation bottleneck? So my answer, I believe, is yes. So I started the process of creating a graph network-based window adjustment implemented in a commercial off-the-shelf FPGA using the most commonly used SLAM algorithm, which is already SLAM 2. So We have our graphical window adjustment, our FPGA implementation, and then the stealing that. So the first iteration is actually creating the graphical network, but then putting it on FPGA. So I'm using a regular Cyclone 10, Cyclone 5, but pushing it down to a Cyclone 10. Why am I pushing down to a Cyclone 10? Because I want to make this into a real small application. I don't want it to be very high, heavy, very small. So at first I was using a Raspberry Pi, so I needed something very lightweight. So I used our MK Vendor, which is Arduino. They have an Intel Cyclone 10 on top. And I used my input sensor was an Intel RealSense E439, which is the RGB depth camera. And then I was going to put that in an RC car, just test it around. So from there, we got to our first prototype. So we have our first picture of what the same Arduino looks like on a 2 gigabyte Raspberry Pi. It looks terrible. This is not good. So we thought we would put a graphical network on top of that, so we tried to put that together, and it didn't work out as well. We did get the car to move though. So let's move on a little bit. So that was the first iteration. Now the second iteration we've been working on recently is what is slowing us down computationally. So we did a pi test basically between 3 different Raspberry Pis. Let me actually go back. So this is the picture that we're trying to recreate right here. Just a regular box. The first picture is on a 2 gigabyte, which we've seen before. We didn't even get the full look close, so that's just out. Then we go to a 4 gigabyte, which is a little bit better, but still not a look close. Now we got the 8 gigabyte, which is actually a full look close. So it doesn't look exactly like the box, but we at least got a full picture. And then we can see the computation operation for the CPU. We're operating between about 77 to 90% of all the Raspberry Pi, which is extremely high. And our memory does go down when we get to the 8 gigabyte, which makes sense. And we only get a full close to 8 gigabyte. But that's still not good enough for us to even put this on a real life application. So now we move to, which Dr. Seaborn, who's my new advisor, actually proposed to me is, why don't you put this on a NUC? So Intel has these NUCs that actually have a lot more computer power. They're not as light, they're a little bit heavier than the Raspberry Pi, obviously, you see the way it is. But comparing to how much power we get to how weight it is, it's actually really good. And we can see that right here. And if I take the same picture, and this is the last one we had, which gave our best results for the Raspberry Pi 8 gigabyte. Intel NUC gives me a more full loop close. Now, is it still ugly? Yes, it is. But it looks just a tad bit better. Sometimes in science we just need a small improvement. What does that small improvement look like? We see, look at the memory, actually. The memory, we're only using 2% of the memory. Why? Because the NUC actually has 62 gigabytes of RAM compared to the Raspberry Pi, which is 8 gigabytes. And then, Intel NUC only use 35% of the total CPU operation. What me and Aaron seen, which was just so great, was that startup time. That startup time for the Raspberry Pi took almost 45 seconds, which is so long. Imagine trying to start up your car and it took that long. Now, when we did the Intel NUC, 6 seconds almost. 12% of the original baseline. So, from there, that gives us a good foundation to say we have a good computing platform to actually do some really cool things. And then incorporate new things like another sensor. So, while we have Intel RealSense, which is our depth camera, that camera still was having trouble tracking the actual object as we're trying to go around. So we're going to lose the object, we lose the detection. So we need something to counteract that. So we have a LiDAR, light detection and range. LiDAR sends a laser, time of arrival, comes back. When the laser comes back, we have the time that it takes. We measure that and we get the distance. So this is a commercial off-the-shelf LiDAR that we purchased right now. So this is what it looks like on a Raspberry Pi. This is what it looks like on a NUC. It looks the same. But what we see on the NUC, we have takes half of the time for it to start up and actually improve. So with understanding that, let's take that LiDAR, combine it with the other system that we had already, switch out the NUC switch out the Raspberry Pi for the NUC, implement our graphical network through the same chain. Now we have more computer power to do more cool things. And then put that on my new improved prototype stack, just to try it around. Now the last part, which I probably have to rush to, I don't have enough time to go through, but how do we do this and how do we make this fun? So now let's talk about we have a LiDAR, right? So having this LiDAR, we're literally just working with laser. Now doing some research, some researchers have actually looked at how can they make an entangled light so where we can actually get a different image that we're looking at when we set up the camera. So if I have my LiDAR here, maybe I'll shoot another laser that's coming out and actually change the different image to get a different image that I'm looking at when I'm on my camera. What is the application of that? Imagine that you're detecting something far away, right? But you need to zoom in a specific part. Using this quantum entanglement principle, we can actually start to make more precise 3D maps because we're able to block out focus on one individual part. So that's the simulation that we see right here. Quantum light on, you see the skater. Without the quantum light, you see the bus. I think I'm out of time right now, but having this power, this very powerful device for the milk, gives us a lot more capabilities to do certain things, such as also with this quantum computing when it comes to actually putting this together. I'll fast forward. Quantum computation would be for the communication aspect. But just in summary, there's a research gap. The research gap is on the Windows problem with computer resources, time, and memory. So my approach, threefold, put in that graph on that proposal, the beginning part, trying to move around their body and change that, put in the note. That's where we're at right now. And then once we get that running, we have a prototype to try and play around, so it's like what I'm saying, what I might have. But at the end goal, this is not just a research project, this is actually to present something that we try to make a quantum sense of something actually physical. The quantum sense that we use for applications, smash out the answer. So in conclusion, quantum sensors are a great playground testing these capabilities of quantum computing and quantum communications that researchers have the most practical experience with them and can be created with hybrid classical quantum systems. There's some of my knowledge, some people out there, especially shout out to Aaron. If you need somebody to go do any type of work, Aaron is one of the best. Please reach out and talk to him. Thank you, Dr. Sebron, Dr. Lou, Dr. Gail, Insulin, and also too for sponsoring this.
All right, great presentation. So, final questions. Very interesting presentation.
Great presentation, thank you. Would it make sense to compare your current GNN approach with a convolutional neural network, for example?
Say it.
Compare the performance of your GNN with a CNN?
Are you saying to compare it?
Yes.
Yeah, so it would make sense to just, it would make sense to compare the fact that I know like there are different types of networks and I'm not saying that I'm good about right now. I just like initially never want to do a comparison, not because I really think about it, I just jump on the way I'm looking at a graph, let me just go straight to a graph. I didn't think deep into the software or the types of networks. I just focused on it. Because mostly like myself, I'm a really powerful guy, so even just doing one graph and then just learning the networks very powerful. So, but once we pretty much perfect that, then we're trying to do something.
Really impressive. I have to work with 7th graders and we do the quantum thing. But that gives you a very good picture for everybody. So the big question is, I know that NVIDIA has GPUs that are portable like Tesla, which are much more powerful than the microprocessors. Can you think about using GPU for
Yeah, so I honestly like we just got the number that we covered like months ago. So like we're already doing just kind of even Dr. Simon told us that they actually got the GPU, like GPU and CPU. There's so much computing on it. But what does better in that realm of changing our base hardware platform, now we can like just like the C and I start testing some of these. So this is our baseline C, and now because we have it, we're able to try and get it up. So definitely we'll expand.
All right, let's thank the speaker. And we would like to thank you guys for coming out to our session. I think we're right on time, huh?